So I'm going to have a fun talk because Peter said all the important things, so I can say all the fun things. General AI, maybe not to use strong AI as a word, is a question of where are we somewhere between these fairly dumb, narrow approaches that are great at optimizing and the very strong AI that we just heard, and I could not agree more, simply does not exist and won't exist for quite a while. To start this out, and you probably hear this from everybody who's been doing AI for a while, it's kind of annoying in the AI hype, all the stuff that is being said about AI. So let's clean up with some of the hype stuff. And I'm going to be more aggressive. Peter was very polite. I'm going to tell you, machines do not understand anything. Like zero. There's no understanding in a machine. What a machine can really do is compare incoming data to a pre-created understanding mechanism or structure. The problem with people pushing that into marketing, and you know exactly that the marketing record is on when somebody tells you, my machine understands blah, blah, blah. The problem with that is that we as humans actually do have understanding, and then we draw conclusions from that. If the machine understands something, it should also know this and that and the other. And we expect the machine to do things that it just will not do. So this is one of the most misleading things that makes people take completely wrong decisions and not just have wrong expectations and be disappointed, but really go down the wrong path. The second thing that is out there, I find personally very amusing, is that all of a sudden everything is modeled after the human brain, right? Just because we have neural networks and we named them that way, we call this as modeled after the human brains. Guys, seriously, if you ever say an AI is modeled after the human brain, please also go out to your former biology teacher and tell them that the amoeba is modeled after the human body. Because it's like basically the same thing. A big neural network has about 1 million nodes. The brain of an average person after puberty has about 84 billion nodes. The neural network needs about half a nuclear power plant to run, and we can do it on 20 watts. Okay, if you look at me, I don't get that, but most of you do, right? So. Also, there's a chemical system. If you go to the after party of this event, try it out. Go to the bar, have a few beers, and see what it does to your brain. There is, with every chemical combination, and there is an infinite number of chemical configurations, your brain gets a new configuration. There's a whole dimension we're missing. So there's definitely we're so much at the beginning of this that we should not talk about it. And then for about 5 years, there's research from the neuroscientists out there that say there's probably also some quantum mechanics going on in the brain, meaning something that injects probability. So even if we can build a neural network as Moore's laws in 2029 that has the size of the brain, we're still missing the chemical system and the quantum mechanical system. We are truly far away from the brain. And an amoeba does not function like the human body either. And the third thing, and I think this was already out there a few times this morning, deep learning is not AI. Well, deep learning is part of AI, but there are more algorithms out there. And by pretending that there is a single algorithm out there, it's not just a bad way of solving problems. It also means that we're definitely in for a new AI winter if we believe that we can solve everything with one problem. I mean, try that with your life. Try solving everything with a problem. Someone is going to be very pissed at you, either your boss or your girlfriend, right? So. There are currently in perception 3 types of AI, right? One being the narrow AIs. This is the stuff where someone takes typically a single algorithm or a small set of algorithms and applies them to a niche small problem. These are great, right? Because they achieve great things. They really optimize. These optimization algorithms are way better than what we had before from statistics because they can live with more free variables, which means either you have to explain less to them or they can deal with more complex problems, but they deal with one problem at a time. My favorite narrow AI, I keep telling this because I love it so much, is a company that trained a neural network to improve tomato growth in greenhouses. You connect your fertilizer, you water your light, poof, you have on the trained network 20% more tomatoes in your greenhouse. If you happen to live in a place where there's not so much sun and the tomatoes don't taste that great, don't have the stupid idea to start growing beans in the same greenhouse because the AI is going to kill all the beans because them stupid things don't turn red. right? This is the problem, and everybody knows this. If you apply one solution that works on one problem really well and take it somewhere else, it probably screws up. I have to say, no one should be afraid of using those narrow AI systems. Why not? Because all of us have been hunting for efficiencies in our personal lives, in our companies for a long time, and why not apply them? There's no black magic to this. This is not Black Mirrors. This is just optimization. On the other hand of the system, we have the science fiction AIs. This is probably what the strong AI, a robot, and I'm going to go down the positive lane here, a robot that actually says, I love you, and knows what that means and actually means it. I can promise to you, no one who is seriously building artificial intelligence, studying that, has the slightest effing clue how to start that project. This is good and bad news. The good news is that ethic and morality just stays with us humans. And the bad news is it stays with us humans. We actually have to deal with it. There is no thing out there that's going to take the question of ethics for us. The whole debate about ethics is just a question that we want to push off being good people to a few programmers or a strange being that does not exist. There is no digital being yet. In the middle somewhere, you have more generalized AI. I chose general, and it's always difficult to choose these terms because it's definitely not strong, but it's applicable. This basically means it's applicable to more than one problem with the same type of engine and the same type of data. Why would you want those? Well, because even in today's world, AIs are not just about gaining insights from data. A lot of people think an AI is good to find some new insight. That's not what it's supposed to do. It's supposed to act. It's supposed to execute. And especially in our old economy, it makes a lot of sense to act because you can automate a lot of processes. Why can you automate a lot of processes? Because it's basically impossible to explain the entire world to an AI. Otherwise, we would have the strong AI. It is impossible, so we can only explain small pieces to an AI and then actually let them run them. Well, what is it that we have done in companies, right? We have tailorized the things to do because we believe in an industrial nation, no person can actually understand the end product, and we've put everything to processes. We have nicely compartmentalized everything that we do, and this is why industrialization as a precursor to AI means that we have finally cut down the economic system in a way where it's accessible to machines. Now we're going to implement it. We shouldn't be so surprised. If you want to build an AI, like anyone can do this. As I said, no black magic. You need algorithms, data. You need talent. That's kind of important. Yeah? And you need compute power. Well, compute power now comes out of the socket. You just get it from Amazon, Google, whoever. Algorithms. Anybody can download AI algorithms. They're just available. They're fantastic algorithms out there. You don't have to find your new one. There are great ones out there. Data. A lot of people have data. Most people have a total misconception what to do with data. And then you have the problem of people. Because building AI typically is not about one single specialty, the people who do this need a broad spectrum. And that's where it gets tricky, because that means that you either need a large team of a lot of people with a lot of different skills, or you need people who are fairly experienced, and both are hard to build. If you look at these single technologies, and I've picked three, and I'm going to explain these three, each one of them, singularity, has a problem, right? So for example, machine learning, which we see in most narrow AIs today, has a simple problem, which is data. There is not enough data to explain the world to a machine. And if you don't believe this, think about it. If you need a 10-year data set to teach something to a machine, you've now taught the average of these 10 years to the machine. The now might be very different. There is never, ever enough data to describe now. This is why pure machine learning has a very natural limit. Then you have natural language processing. We see this in all the chatbots and so on. Language is kind of the end product of evolution. Like 4 billion years of testing and trial and error went into this. All of the natural language stuff you see, and I absolutely love the Siri video, just shows you it's a simulation still. It's a total simulation. It works super well when the machine knows what you're trying to do. If you have a number where people call in sick, and they use different words like, I'm sick, I'm under the weather, I'm not feeling well, and so, yeah, this works. But if you want to have a general conversation, this does not work at all. So there is a total boundary to this. And then you have the machine reasoning, including case-based reasoning and so on. This is a fantastic system because we're able to plan into the future and then weigh optionality against each other. The problem is maintaining these rule bases is a tough job, and the tough job means that you actually have to live around with a lot of effort to doing it, and then oftentimes, if you are trying to walk out of a narrow space with an expert system, you are most likely going to outperform maintenance as compared to benefit. So there's more maintenance than benefit, and then you don't do it. Let's have a look about how these algorithms roughly work, because everybody is talking about it, and I feel that a lot of people don't know what's inside of it, and maybe we can have a little chat about this. So number one is, if you have lots of incoming data from sensory organs like cameras or lidars or eyes and ears and noses, and you put them in a processor, and the job of that processor is to find a pattern in this data and then associate a positive action with that. This is basically what we do in machine learning, and this is also in the world of biology what we call instincts, right? In an animal, we would say if it sees a tiger and runs away, that's a very good, it has recognized the pattern tiger, and it knows that it has to run away. Why? Because all its companions that did not have this reflex of running away were eaten. That is backpropagation in nature. Basically, these are rules, right? If tiger, then run. But these rules can be encoded and compressed. With us, it's very simple, right? I can explain to you how math works. I definitely can't explain to you how I can make my heart beat, because that went from the brain to the nervous system to the nerves around the heart, right? The longer you live and the longer you process these things, the more they get ingrained into your system. And this is exactly what happens with neural networks. Basically, here you have machine learning written down as finding patterns in data and associating a positive action with that, and then compressing it into some mathematical structure. Now, the best of these systems, they are able to conceptualize. It's always about outpacing the evolution. Outpacing, this is the purely evolutionary process, right? Everything that doesn't go for the survival function dies. Outpace the evolution, for example, with concepts. Concepts means that if you have associated the action of eating with the pattern of herring, and then you say like, I've got a lot of things that look like herring, let's associate eating with all of them. And then all of a sudden you only have to learn the exceptions, whereas don't eat the Japanese roundfish because you die. Same mechanism, but as there are more edible fish than poisonous fish, you have now outpaced evolution because you didn't have to go through these 70,000 or whatever repetitions to learn which fish you can eat for each fish. You made an assumption. A lot of higher animals have done this. What we as humans have done, something fantastic, we have created language. We are able to put all that experience that we gathered into words and pass it on to someone else, and they don't have to trial and error it at all or have children in order to propagate that knowledge. We can actually just tell someone. Okay, for those of you with children, you probably know that just telling someone normally doesn't help, but the amount of repetition goes down dramatically. So when you tell your child is, don't touch that, it's hot, but it doesn't touch it 70,000 times. One will do, right? So this is what we can do with language. And it's quite amazing. And the knowledge, what has not been so compressed that we can't express it anymore, all of this expressible knowledge, the conscious knowledge that we can symbolize through language, is accessible to us, and we can pass it on, and we have outpaced evolution dramatically. This is what natural language processing is supposed to do. And if you want to, like my personal estimation, we're about at 1%. Like we're nowhere close to what is actually possible in dialogue and so on in technique. Then I said this is what makes humans different, like the Homo species as compared to other animals on the planet. Then there's the third type of algorithm, which we said was reasoning. if we want to say this nicely, we have outpaced evolution again by having fantasy or imagination. If you want to say that a little more scientifically, we are able to plan the future in our heads and weigh options against each other and make a good choice. We actually do this in our heads. Everybody has about 700 words per minute in their heads, making constantly an argument of what to do and what not to do. Geniuses have a little more, other people might have a little less. But basically that it is. And now you can inject goals that are beyond survival. Inject them, meaning you don't set them yourself. Like does not include consciousness at all. This does not include self-awareness or anything like this. But we've now explained the ability to learn by trial and error, the ability to communicate something that you've learned, and the ability to weigh in a special situation something that you've learned against each other. These are 3 algorithms. I hope we can agree that if you want to be a little more general than just applying like one thing to one solution, which you can do well, you probably need these 3 types of algorithms. Here's what we can do today in terms of more generalizing. You can use machine reasoning to compartmentalize the space, because people give you knowledge that you're in. Unfortunately, people that give you knowledge typically will not give you the full explanation of logic. Like, as a computer scientist, you want a precondition, a postcondition, provable space, right? This does not exist in people. People will assume that there is context, and according to this, like, it's actually weird that we don't have more fights, is because we are so good at interpreting context. We basically use these type of algorithms to compartmentalize the space and reduce the amount of data you need for machine learning problems. And then you use the learning to deal with ambiguity or unexpected events and stuff like that. You can use a chatbot to extract knowledge from people, so you avoid having to learn everything just by observation. And you can use a semantic database to store all the experience that you already had, so that your next step in reasoning and your next step in machine learning has it easier. And this is the actual point. The economic effect as compared of a narrow AI application and a more general AI application is that the amount of time you need to put the machine to a new problem basically goes down logarithmically, or exponentially, like reverse exponentially. This is the actual application. We cannot go further than that today. But that's pretty good, right? So if your first project takes 3 months, and the next one takes 1.5 months, and the next one takes, and so on, right? You can actually get shit going pretty quickly on different problems. But it is still exactly what Peter just said. It is a single problem at a time approach, and because we can refer to all the stuff that is already in the system from the other problems, we just make that making these problems accessible and automatable faster. So I think that we have a lot of questions about these AIs. We have to deal with 3 big problems that AIs totally have. 3 big problems. The problem is not finding the right data set and so on. There's 3 problems that you have to think about when you're thinking about general AI. One is Moravec's paradox, meaning that it is easy, whatever is easy for a human is hard for a machine, and whatever is hard for a human is probably easy for a machine. This is a simple evolutionary fact, because whatever is easy to us, we've been practicing for 4 billion years, even the crocodile could walk, right? And whatever is hard for us, like, let's say, non-Euclidean geometry, we've only known this for 70 years, most people get a headache from that. This time is easier to catch up for a machine. This is a true problem because we expect machines to do stuff that is easy for us as well. The second question is little data. As people, we're constantly making decisions, actually pretty good decisions, with way too little information. That's what AIs have to do as well, and they have to feel confident about it, which is very hard to do, because in the end, confidence is math, and if you simply don't have enough things to fill into your equations, how can you solve them? And the third thing that would really make a general AI take a big leap is knowledge transfer. If you can learn something in a game, and you know that with our AI, we've, for example, played Civilization, the machine has learned the process of how to choose the spot for building a city. we can post-data analyze. We can see that the decision process that it has taken is exactly the same process that a real estate customer of ours has taught the machine to which objects of real estate to look into to make the decision. But the data is far from being connected enough so this knowledge could transfer automatically. Yeah, so we can see that this is possible in the future, but it's definitely not there yet. Data is important, and you have to pay attention that your data stays with you. I'm actually a favorite of those people that go with the EU and say we need data protection. But we need data protection because data is a tradable asset, because it's a way to explain the world to machines. The problem that is not part of the data is the oil of the 21st century religion that is being pushed around is that data is a tradable asset, and you need to share and trade it, because a company like BMW has all the data that the company like Schraubenwirt needs to build a better screw. It has very little data, next to zero, on how to know what a car to do next. This is why it makes total sense. If you produce data, it should be yours because you can trade it in the future. Data, ladies and gentlemen, is not just there to do predictive analytics. Actually, predictive analytics is just the fancy name for linear regression. People were too embarrassed to actually say, like, we're doing these things that we know for 30 years, right? So they've renamed it. Data is there to explain the world to a machine. And in order to do that, you need structured data. And if you want to extract structure from non-structure, you need a lot of data. And there's two ways to do this, right? You can collect the data by sitting on the shoulder of a consumer and watch whatever they're doing. You get a very superficial picture, but you get a picture of the entire world. Or you can sit inside industry, you get a very deep picture, but a very narrow one, because each company only does a very narrow thing. This is why data needs to be interchanged. There's two ways of teaching a machine. There's two ways of getting knowledge into a machine. You can have observation and trial and error, which is the data-heavier approach, or you can have communication with the machine. You explicitly give exact, unexact, whatever information to the machine. I'm very surprised that most companies try the trial and error and observation route for the first time, because most companies exist because they already know something. Why can't they communicate what they already know to a machine first? Transferring knowledge you already have and then learning what you don't have or don't express by trial and error and observation has an energy advantage of 95%. Like, machine learning actually is not very energy efficient. If we think about AI, we shouldn't think about insights into data. We should think about our experience. If a machine looks at us and tries to replicate what we do, or if we teach something explicit to a machine, we make a machine use our experience. Maybe it can recombine the experience in different ways, making our experience executable. It's about execution. It's not just about insights. Thank you very much.